Find the volume of the solid formed by rotating y is equal to the natural log of x about the y-axis bounded by x is equal to 1 and x is equal to 3. At x equal to 1, the natural log of x is equal to 0. So therefore that is x is equal to 1. Okay, and this here is x is equal to 3. So we are finding the volume when we rotate this function here that sits between these 2 points about the y-axis. So between these 2 points, we obviously also have the x-axis that's bounding it from underneath. And then the upper bound is the natural log of x. So if we rotate this portion that I've shaded in about the y-axis, what we'll have is a shape similar to the one that I've drawn. And I hope it makes sense to you, or intuitively you can kind of see what this looks like. It looks like a cylinder, and in the middle it looks kind of like a sloped funnel leading into this little circle that should sit somewhere at the bottom like that. Okay, so the way we're going to do this is with integration, and we're going to use the cylindrical shells method. So what that means is we're integrating between 1 and 3, and now what we are integrating is the surface area, the outer surface area of a cylinder. So that's basically a cylinder that excludes the 2 caps. It's just this outer area of the cylinder. And so what is this outer area of the cylinder? Well, it's 2 pi r times by the height. Okay, and the reason why is because 2 pi r is the circumference of the circle, and the height is obviously that length over there. So 2 pi r times by the height, if we unravel this, is basically the area of a rectangle. Okay, now we need to find out what our radius is and what our height is for each of the cylinders that we're going to fit into this diagram. So that's essentially what one of our cylinders will look like. And then, of course, we'll keep drawing these cylinders, and we'll keep going outwards and getting bigger and bigger cylinders. And we'll add up the surface area of all these cylinders using integration. So that's essentially what integration does. It adds up the area of all these cylinders, the infinite number of cylinders that lies between x is equal to 1 and x is equal to 3. And if we add up all these areas, we will approach the volume. And now, therefore, our answer to our integral will in fact be the volume of this solid. Okay, so let's write down an integral. So our integral for volume is integrated from 1 to 3, so it's a definite integral. And then now we have the surface area of our cylinders, our cylindrical shells. So our radius is over here, and we need to write our radius in terms of x. Okay, so our radius is going to be from this point, or the origin, to whatever cylinders outside we are integrating. So that'll be given by the x value. So if we were here, the x value might be 2, and so the radius of the circle that goes over there is going to be 2. So our radius is x. Now our height at, for example, 2 is going to be the natural log of 2. So our height can be expressed as the natural log of x, generally. And then that's in terms of x. We're doing the integral in terms of x. So going on to solve this integral, we can use integration by parts, and u is the part that is easier to differentiate. So we'll let it be the natural log of x, and then dv is going to be the part that's easy to integrate. So we'll let that be x. And now, differentiating the natural log of x, we get the derivative of u in terms of x is 1 over x. Then integrating this, v will then be x squared over 2. Okay, now expressing our integral, we get x squared over 2 times by the natural log of x, and that's uv. And don't forget, everything now is going to be multiplied by 2 pi, because I've essentially taken that out of my integral, minus the integral of v du. So that's x squared over 2 times by 1 over x. And x squared over x is just x. So that's x over 2. But I can take out that 1 over 2, and now we're integrating just x, and that's integrated from 1 until 3. Those are our limits of integration. Okay. So solving this integral, we know it's going to be, the integral of x is x squared over 2. So I can erase all of this, and I can insert here my x squared over 2. And then x squared over 2 times by negative 1 over 2 is negative x squared over 4. And then if I distribute this 2 pi, these 2's will cancel, and I'll be left with pi x squared, and then 2 pi times by this, my 2 will cancel with that, and we'll get 2 in the denominator, so we'll have pi x squared over 2. Okay, now all that's left to do is to substitute in our limits of integration. So first substituting in 3, we get 3 squared, which is 9, so we have 9 pi times by the natural log of 3 minus, and then 3 squared again is obviously 9, so that's 9 pi over 2. Now we subtract when we substitute in 1. So when we substitute in 1 into this, we get 1 squared, which is 1, so that's pi times by the natural log of 1, minus 1 squared over 2, so that's 1 over 2 times by pi, so it's pi over 2. And then the natural log of 1 we know to be 0, so that whole term is going to be 0. And then this whole bracket, we can simplify it to just be plus pi over 2. And obviously get rid of that. And then negative 9 pi over 2 plus pi over 2 is negative 8 pi over 2. And negative 8 pi over 2 is negative pi by 4. And we have now arrived at the solution to our integral and the volume of the solid. Thank you for watching.